Hi. So in this class, we're going to be talking about the weak form of the elasticity equation or the elasticity equilibrium equations. Okay, so previously we went through we started to define the terms for the problem at hand, in this case a problem of elasticity, and we ended up writing the strong form for the equilibrium equations. So the strong form for the equilibrium equations is the gradient of the stress tensor, and when you write it down in void notation, you end up using this operator here as a differential operator. Okay, please note that this operator right here contains a correction from the previous video. The previous video had some errors here, but this is the final correct one, and the errors were around here. You can see a little bit of changed those around. So the first equation here is the gradient of the stress field, or the stress tensor, is equal to the body forces. Okay, and then the second equation is the constitutive equation, where we have simply Hooke's law. And finally, we have a kinematic relationship that relates strains, small strains in this case, with displacements. So this is a strain displacement relation, right? And on top of that, you need to add the essential boundary conditions, such as fixed boundary conditions, anywhere basically where the solution is known, U is known. And then you can have natural boundary conditions, which is whatever is not an essential boundary condition. In this case, we're going to focus on those two. In this case, traction vectors, for example, are an example. Traction vectors are specified, basically, it's a specified stress field in a particular direction. So you take a normal, this is the outward normal of the domain, and you're saying that the stress tensor projected along the direction of the normal is equal to some given traction. That's a natural boundary condition. So now we want to write these equations in weak form. So what is the weak form? The weak form is also known as the variational form of the equation. And in this case, there's two ways to go about it. One way is, for any PDE, for any partial differential equation, you can write, there's a specific set of procedures what you can do to the equations to turn them into a weak formulation. In this case, I want to give the more intuitive notion using the principle of virtual work. Okay, so the principle of virtual work is just another way to state equilibrium. Okay, so we're going to use principle of virtual work, right? When we state equilibrium using the strong form of the equations, so here you have what I was talking about here. You have the gradient of the stress tensor is equal to the body forces. What this means is that this is a point-by-point statement of equilibrium. So you have a body, okay, and you're going to say this body is in equilibrium if at each point P with a specified set of coordinates, I compute this derivative of the stress tensor, and it's going to equal whatever the outward or the body forces are. So if you want to say the whole body is in equilibrium, that's fine. You say for all omega, this must stand, and this is what we're saying here. So these three conditions are for all x in omega. Whereas the approach for the weak form is a little bit different, and you'll see why. But just keep in mind that uh, the strong form basically tells you about, for all points they must meet this differential condition. And yeah, okay. So what is the statement of the principle of virtual work? So basically, I'm just gonna add the essential boundaries. Yes, I'm gonna add the possibility to have some traction vectors like this, some specified traction field. We're at a point P. At that point, we have a B body force defined of whatever the coordinates are. And this is your gamma natural. Okay. So if you think about it, so let's say we apply these forces, the body forces and the tractions, we apply them instantaneously. Okay, so here is an undeformed configuration. That means this is the shape of the domain right before applying these forces. And then as soon as you apply the forces, this domain is going to stretch maybe a little bit. It's going to change shape. So you have maybe something like this. And I'm just assuming here that this is a zero boundary condition. So this is the deformed or displaced configuration. Okay. And for each point P, so if this is P, this is going to end up at a point P prime, and the vector field that takes you from P to P prime is the displacement field. So we talked about that when we were stating the strong form of the equilibrium. Now, so what does the principle of virtual work say? So it's basically a statement that says, in this case, or in any case, if the body is in equilibrium, then it's going to meet the following condition. It's going to be able to do the following. So let's say the deformed displaced configuration, I apply an increment to that deformed or displaced configuration. So we're going to move this a little bit, tiny bit. Again, paying attention that the essential boundary conditions are met. So essential BCs are enforced. So you basically take the deformed shape and jiggle it a little bit, move it around, stretch it a little bit. And this is the virtual displaced or the virtually displaced configuration. It's a virtual displacement. And P is going to end up with a little delta U. It's going to end up in a P double prime at some other point. Okay. Now the thing is, you can choose this delta U, the shape, the new shape, the virtual shape you apply. As long as it's small, you can make it whatever you want. Okay. So you can displace the domain omega in any way you want about the deformed or displaced configuration, the true solution basically. You add this little, and then if you compute the work done by the internal forces due to this displacement, the virtual displacement of the body, it has to equal the external work done. So basically what it's going to say here, it's going to say when I do this virtual displacement, so I take on top of the deformed shape, on top of the black line, I test a little bit. I switch things around. I move the domain a little bit. Then that movement is going to be such that, or it's not going to be such. If the body is in equilibrium, then this applies. So this implies equilibrium. So if when I apply the virtual displacement, if I compute the internal work of the forces undergoing the stresses, I mean, when you do that displacement, and then I compute also the external work of, in this case, the traction field, when I undergo those displacement, then those have to be equal. And that, if those are equal, that implies equilibrium. So remember I said that the strong form statement, so this is gonna lead us to the weak form. The strong form statement is you go at every point inside your domain and you compute that gradient, and if you have that the gradient of the stress field is equal to the body forces, then that's equilibrium at each point. That must be met at each point. In this case, this is different. In this case, if we're at equilibrium, what you're saying is something is that any small motion about the deformed configuration will and here I mean any deformed. So as before, you were talking about all the points have to meet the gradient condition. In this case, all the possible deformations must meet this if the body is in equilibrium. So this must apply to all of the deformations. Sorry about that. And I'm back. Okay, so let's start over. As I said previously, the strong statement, so the statement we had in the previous case, this one, in this statement, you move around every point inside the domain, and if the domain is in equilibrium, then it must follow these three equations. So the gradient of the stress field must be equal to the body forces if we have all these other conditions. So U is going to be a solution, and the solution is going to be in equilibrium if when you compute the strain field and then you go and compute the stress field and then you take the derivative of that and you equal it, it's going to be equal to the body forces. Okay, that's a strong statement, and that holds for every single point of the domain. In this case, in the case of virtual work, you have the following statement of equilibrium. You say, okay, U is going to be a solution of this problem. That is, the problem is going to be in equilibrium, the system is going to be in equilibrium with that black line, that's the form of displacement or displaced configuration. If the system is in equilibrium, then if I jiggle the deformed shape a little bit, if that means if I displace it a little bit more by this delta, and then with that displacement I compute the work done by the internal stresses, those must equal the work done by the external forces. And this is a statement of equilibrium. If this holds for a particular delta U, then equilibrium. But this must hold independent of what delta U is, independent of what virtual deformation, independent of what way I wish to jiggle the domain a little bit. So for all possible configurations. Okay? So that's how it's different. The previous one holds for all points in space, the gradient is equal to the boundary forces. In this case, the internal work is equal to the external force, work for all possible deformed virtual, for all possible virtual displacement fields I can think of. So it's a vast space. Okay, and this leads to the weak form. So let's just put some equations here. What's the work done? So if I have delta U is a virtual displacement field, okay, then this virtual displacement field produces virtual strains. So going to produce a virtual strain field, which is going to be equal to D applied over delta U, and this is the virtual strain field. Okay, and on the other hand, we have sigma, which is a real, or the solution, right? The real stress field. So this is the one that's going to do work. So the internal virtual work is the real stresses, internal product, internal tensor product, with the virtual, working over the virtual strains, and that for the whole body. Sorry, I'm using a V here. I should use omega because that's what I'm naming this domain. Omega. Okay, so that's a statement. This is tensor notation, so this is basically going to resolve into sigma xx delta epsilon xx plus sigma xy times delta epsilon xy, and so on, for all the components of the tensor. In void notation, you can write this as follows: integral over omega. You can say delta epsilon transposed multiplied by the sigma vector in dv, or d omega. Actually, let's use omega here. Okay, so this is the statement of the, and this, this can be further developed into d, the differential operation, applied over the stress, so over the displacement field, and that gets transposed sigma. Okay, we'll need that later. Now the other side. Okay, so here's why it's important that the essential boundary conditions be enforced, because now we're going to compute the external work. The external work, work is force times displacement. Okay, in the case of internal work, the forces are the stresses, and we're using as displacement the strain field. Okay, in the case of the external forces, we have the tractions. These tractions, they're going to do virtual work with whatever the displacement field, the virtual displacement field is at the boundary. So basically what this is that force, so integral over the essential, the natural boundary conditions. Let's erase that. So gamma natural of the traction vector dot product the virtual displacement field in ds, because it's a differential of surface, we're just going around. And at the essential boundary conditions, we know that there are reaction forces. We know that this part, there's some sort of forces that enforce that boundary condition. But since we require that the delta U, that is the virtual displacement of the body, meets the essential boundary conditions, that means that there's not going to be any displacement there. And that means that these reaction forces, while they're there, they are not part of the, they don't do work, so they don't appear in this equation. Okay? In void notation, we can write this as integral over gamma natural. We're going to just do delta U transposed T ds. This is a vector, xy or xyz, depending if you're in 2D or 3D. T is sorry, is another vector. Okay, so the weak form of the equilibrium equations is basically that which I have already written on the other side. Integral over omega delta epsilon transpose sigma d omega has to be equal to integral over gamma natural delta U transpose T. And I missed something. Over here in the external forces, the other thing that does do external work is the body forces. So we add here a term integral over omega, body forces du, and this one is over d omega. So we're going to add that term here, plus integral omega is going to end up being delta u b d omega. And that's the weak statement of the differential equation. Next up, we're going to talk about how to use this and a finite element discretization to write finite element equations, and then we're going to specialize those equations for particular elements and start doing real stuff with that. Thank you.